Assalamu alaikum dear students. I hope you are all fine by the grace of Almighty Allah. I welcome you all to the 23rd lecture of Thermodynamics 2. Lecture 23. The contents of lecture 23 are here we will discuss the summarized or chapter of Exergy, then we will solve some numerical problem and we will discuss conceptual question answers as well. So loss in available energy. So as you know that available energy and unavailable energy runs parallel to each other because they both combine. So available energy and unavailable energy both sum up to make the total form of energy. So as there is a loss in available energy or decrease in available energy, then on the other hand there will be an increase in unavailable energy. So decrease in available energy when heat is transferred through a finite temperature difference. Loss in available energy. So all three when there is written decrease in available energy, loss in available energy or increase in unavailable energy, all these things means the same. And when we are talking about finite temperature difference, then it means we are talking about a body, so the temperature of body will reduce. So here two bodies are shown, one is at temperature T1 and other is at temperature T2. So consider a body as shown. So here a body is shown. Let the initial temperature of body is T1. So T1 a body is initially as temperature T1. So you may give that a number of 100 degrees centigrade, and at this temperature the available energy is available energy 1. So at state 1 the temperature of body 1 is T1, and at that temperature the value of content of available energy for body is AE1. So some of the heat is ejected from body and the temperature of body is reduced to T2. So Q amount of energy from body is rejected to the atmosphere and the temperature of body is reduced, and now the temperature is T2. For example, let the temperature of T1 is equal to 100 degrees centigrade. A certain amount of heat is ejected to the surrounding. Now the temperature of body is 80 degrees centigrade. And at this temperature of T2, the available energy of the body is AE2. So at 80 degrees centigrade, the available energy of the body is AE2. So AE1 is greater than AE2 because T1 is greater than T2. So here a reservoir T1 is shown and Q amount of energy is entered into the heat engine. W useful is the amount work that is produced by heat engine, that is the available energy 1, and Q naught is the amount of unavailable energy, and Q naught is the amount of heat rejected from heat engine into the surrounding, that is at a dead state. Now for case 1, when temperature is T1, so at T1 the temperature is T1 and the available energy is AE1. So here Q is the total amount of energy, AE1 is the available amount of energy, and Q naught is the unavailable energy. So for case 1 the available energy is AE1. Now case 2, so here you see that the certain amount of energy is lost to the ambient and Q amount of energy that is entered into the heat engine. But now the temperature is reduced. So for example, in the last slide, the temperature of reservoir is 100 degrees centigrade, from which the heat is entered into the heat engine. So now the temperature of T2 reservoir is 80 degrees centigrade, and Q amount of heat, the same amount of heat is entered into the heat engine. Now Q is the total amount of energy, and for case 2 the available energy is AE2, and Q naught is the amount of energy that is rejected into the surrounding. So now we will discuss some conceptual question answer. Can we have any energy transfer as heat transfer that is 100% available? So the possible amount of work that can be obtained equal to exergy or availability. So as you know that exergy is the maximum amount of work that can be obtained. The maximum is limited to that, or if the reversible heat engine, if we have a reversible heat engine and we have an actual heat engine, then the maximum amount of work that can be produced by a reversible heat engine is the amount of exergy or availability that we can achieve from any system. So when we are transferring energy in the form of heat, so 100% energy is not available, because the formula is 1 minus T naught over T into Q. So to get the 100% efficiency, we have to uh, produce an infinite amount of high temperature in the high temperature thermal energy reservoir, which is not possible. Therefore, to transfer 100% available energy is not possible. Its electrical work is 100% available. So yes, electrical energy is a high grade form of energy, and it has 100% exergy or availability. So electrical work is 100% available. So in the last slide, heat transfer or heat energy is not 100% available, and in the current slide, electrical work is 100% available. A nozzle does not have any actual work involved. How should you then interpret the reversible work? So here we have been asked that how you will represent a reversible work when the fluid is flowing through within the nozzle. So the purpose of nozzle is not to make work but to increase the velocity, because you know that the function of nozzle is to increase velocity and decrease pressure. So here the answer suggests that the function of nozzle is not to produce work but to increase the velocity or kinetic energy. Hence reversible, if we are talking about the reversible nozzle, then the energy or kinetic energy produced within the nozzle or increase in the velocity will compensate the reversible work. So let's suppose we have two form of nozzle, and we have two nozzle, one is an actual nozzle and one is a reversible nozzle. So if the exit will for same initial inlet condition, the exit velocity of actual nozzle is 25 meter per second, then the exit velocity of reversible nozzle will be greater than 25, and the reversible work will be equal to the possible total kinetic energy output of the reversible nozzle. If an actual control volume process is reversible, what can you say about the work done? So the work done is maximum possible. If the work is positive, then it is maximum possible work out, and if the work is negative, so it is a minimum work possible that must be supplied. So conceptual question answer. So the Conceptual question answer is we cannot create nor destroy energy. Can we create or destroy exergy? So we know that the available energy, so energy is equal to available energy and unavailable energy. So energy is the sum of available and unavailable energy. So available energy is also known as exergy. So it is asked that energy cannot be created or destroyed, but can available energy can be destroyed or created? So available energy cannot be created. However, if the process is irreversible, then the value of available energy is reduced. So more the irreversible process is, the lesser the value of available energy. So that the decrease in the available energy is replaced by the term entropy generation. So the destruction or reduction of exergy is directly proportional to the irreversibility of the process. So as the process is more and more irreversible, the value of exergy is keep on decreasing. So the value of exergy cannot be created, however it can be reduced and destroyed as the process more and more becomes irreversible. So in a turbine, what is the source of exergy? So the flow into the turbine is the source of exergy. So the fluid or working fluid that is entering into the turbine provide the source of exergy or available energy. So if the fluid that is exiting the turbine also contains some amount of exergy, then the net amount of exergy will be the sum of exergy that is entering and leaving the system. So let's suppose a fluid with the 100 joule of energy enters the turbine, 40 joule of energy is converted into work and 60 joule of energy is at the exit, and the difference 100 minus 60 will equal to the amount of work done or useful energy. In the pump, what is the source of exergy? So as you know that the pump is a work consuming device, therefore the amount of work that is given or done on the pump, for example if the shaft work or the reciprocating work is done on the pump, then the amount of energy that is supplied to the pump is utilized to increase the pressure of the working fluid, as the main function of pump is to increase the pressure of the fluid. Therefore the amount of energy we are inputting into the pump or introducing or connecting the pump, for example if we are introducing it with the connecting with it into the electrical energy, so the amount of electrical energy supplied to the pump is utilized to increase the pressure of the working fluid. So in a heat engine, what is the source of exergy? So as you know that heat engine is a work producing device. So a certain amount of heat is entered into the heat engine. Some of it will be converted into work and other will be rejected into the atmosphere. So the amount of energy that is entering into the heat engine is the source of exergy. So if that amount of energy is entering into the that is entering into the heat engine is coming from a source, uh, it may be a finite body or it may be a thermal energy reservoir, so that will act as a source of exergy. The conceptual question answer continues, and the next one is the energy of the ocean is available? So the short answer is no, because the ocean is at atmospheric temperature. So when we are talking about in terms of energy in terms of thermodynamics, then we are talking about the energy, so the thermal energy that can be converted into work. So we have our producing device, like if you're talking about the heat engine, then heat engine work on the temperature difference principle. So high temperature heat is entering into the heat engine and some of it is converting into work and other is leaving into the ambient or rejecting into the sink. So as the heat engine require temperature difference, but the ocean cannot provide the temperature difference because it is present at the ambient temperature. However, when you will be studying the renewable energy subject, then you will came to know that there are certain other method to absorb or to convert the ocean energy into useful work. So it may require the wave energy or tidal energy. So certain devices are present that convert that energy into electrical energy and other form of energy as well. However, in a certain portion, in a limited time span, if you can find out a temperature difference within ocean, then you may utilize a heat engine to convert or extract energy from the ocean, but that will be a very limited case and with a very limited time span. So conceptual question answer. In an actual control volume process is reversible, what can you say about the work done? So you are asked about the reversible work. So as you know that the reversible work is the maximum amount of work that can be produced with the process. So if the process is a work producing, so if the reversible work is the reversible process, a work producing process, then the work produced is the maximum amount of work. And if the device is work consuming device, then the work supplied will be minimum. So for the reversible process, if the device is work producing, then work obtained will be maximum. And if the device is work consuming, then the work supplied will be minimum. Can entropy change in a control process that is reversible? So you are asked if the process is reversible, will the value of entropy will remain constant or it may can change? So the short answer is that the entropy can change for the reversible process as well. So a flow in or out at a state with a different entropy than the average entropy inside, or a heat transfer will change the entropy. So a certain amount of heat added or leaving the system, or the entropy, the heat transfer within the process will also change the entropy of the system as well. So all the terms that change the entropy are transfer terms, so there is no net increase generation of entropy. So as you know that the entropy mechanism or transfer of entropy mechanism consists of mass transfer and heat transfer. So the overall entropy for the reversible, because due to reversible process there will be no entropy generation. So the entropy will overall entropy of the system will remain constant, but however within the system the entropy can change. So energy can be stored as internal energy, potential energy, or kinetic energy. Are those energies are 100% available? So the answer is the internal energy is only partly available. A process like expansion give out work, or if it cools by heat transfer out, only partly available as work. So you are asked that there are three basic type of energies: internal energy, potential, and kinetic energy. Which of that will is 100% available? So internal energy is not 100% available, rather it is partly available. And for potential and kinetic energy, these are 100% available. But as the kinetic energy is depend upon the motion, so there may be a certain loss of kinetic energy due to the mechanical work or the frictional loss due to the motion of mechanical equipment. We cannot create nor destroy energy. Can we create, destroy exergy? So that is another conceptual question answer. So the answer is yes, every process that is irreversible to some degree destroy exergy. This destruction is directly proportional to the entropy generation. We cannot create exergy. It remain constant in the case of reversible process. So the question asked was, can exergy or available energy be destroyed? So as you know that available energy is limited to the irreversibility of the process. If the process is more and more irreversible, then the available energy will reduce and reduce further. So irreversibility will generate a term that you know that the entropy generation term is introduced due to the irreversibility of the process. So as the entropy generation is increased due to the more irreversibility of the process, so as more the process is irreversible, the entropy generation term will be greater and exergy term will decrease. So in only in the reversible process the exergy will remain constant, but in the irreversible process, as more the irreversible process is, the exergy is decreased. So the numerical problem is, during a thermodynamic process, 100 kilojoule of heat is transferred from a reservoir at 800 Kelvin to a sink that is at 400 Kelvin. The ambient temperature is 300 Kelvin. Calculate the loss of energy. So here a heat engine is connected to a source and a sink. So initially a source that is at temperature, a thermal reservoir that is at temperature of 800 Kelvin is connected to another thermal reservoir that is at a 400 Kelvin temperature, and then that thermal reservoir is connected to heat engine, and that heat engine is connected to sink that is a temperature of 300 Kelvin. Heat engine will produce a certain amount of useful work. So now the question is to calculate the loss in the energy. So initially the heat engine was first connected to 800 Kelvin reservoir, and then in the case 2 the heat engine is connected to 400 Kelvin temperature reservoir. So we want to calculate what is the loss of exergy when the heat engine is connected to 800, and then what is the value of available energy when it is connected to 400. So the difference of available energy when the heat engine is connected to 800 400 Kelvin reservoir will represent the loss in the energy. So here loss in the available energy is the available energy 1 minus available energy 2. So available energy 1 is the one that when the heat engine is connected to 800 Kelvin temperature reservoir, and available energy 2 is the energy that when the heat engine is connected to 400 Kelvin temperature reservoir. So here we have already uh, know this relation, we have derived this relation, so we have to only plug in the values. So T1 is the temperature of reservoir that is 800, and T2 is the temperature of reservoir that is 400 Kelvin. So loss in the available energy is 37.5 kilojoule. So that is the same numerical, but that is a different methodology. Here we have utilized the value or relation for the change of entropy. So now we know that the entropy change for the reservoir is Q by T. So T1 is the temperature 800 and T2 is the temperature 400. So when we plug in the value, we have the same answer as in the previous slide as well. So calculate the available and unavailable energy in 40 kg of water at 75 degrees centigrade with respect to surrounding, that is at 5 degrees centigrade. Pressure of water is 1 atm. So here we have a certain mass of water, there is some certain temperature, and here we have a surrounding that is at certain temperature. So heat is exiting out of the water. So here we have to calculate the available and unavailable energy. So Q is equal to mCp delta T. That is the relation we have already known. So the difference of temperature is 75 minus 5 degrees centigrade. So as that is a difference, so we don't need to convert that into the Kelvin scale as well, because the difference of Kelvin and centigrade is same. So we don't need to convert that into the Kelvin scale. So the value of Q is 11760 kilojoules, and here we are calculating the Exergy value. This relation we have already derived that. So mcp T minus T naught natural log T naught over T. So here T is the temperature of water and T naught is the temperature of the surrounding. When we plug in the values, so the value of Exergy is 1340 kilojoule. So Q is the total amount of energy that is present within the water. Exergy is the available amount of energy. The difference of total energy minus available energy is equal to unavailable energy. So the difference of total minus available is unavailable energy. So when we subtract the both, we find the value of unavailable energy, that is 10420 kilojoule of unavailable energy. So the next numerical is for steady state process from state 1 to 2, enthalpy changes from H1 to H2. H1 value is 400 kilojoule per kg and H2 is 100 kilojoule per kg. And entropy changes from S1 to S2. S1 is 101 kilojoule per kg Kelvin and S2 is 0.7 kilojoule per kg Kelvin. The surrounding temperature is 300 Kelvin. For negligible change in kinetic and potential energy, find the change in availability of the system. So that is a question. We want to find the availability of the system. So here the change of availability is equal to exergy of the system. So we know the relation. So delta H is equal to T naught delta S. So we know all the values of H1, H2, S1, S2, and T naught is the temperature of the surrounding. We plug in all the values. So state 1 enthalpy, state 2 enthalpy, surrounding temperature, state 1 entropy and state 2 entropy. So the value of Exergy is 180 kilojoule per kg. So that is the last numerical for the lecture. Air expands through a turbine from 500 kilopascal 520 degrees centigrade temperature to 100 kilopascal and 300 degrees centigrade temperature. During the expansion, 10 kilojoule per kg of heat is lost to the surrounding, which is at 98 kilopascal and 20 degrees centigrade temperature. Neglecting the change in kinetic and potential energy, determine the following. So here we have to calculate the decrease in availability, the maximum work, and the irreversibility. So here you can see the turbine schematic diagram is shown. The inlet properties are on the left hand side, the outlet properties are on the right hand side. The Q amount of energy that is lost into the environment is shown by the arrow. The properties of the environment or dead state are also mentioned here. So decrease in availability, change in availability, or loss in the available energy or work done by the turbine in this case, all these four things mean the same. So in the question here it is asked to you that to calculate the decrease in availability. So it may be mentioned here as you want to calculate the change in availability, loss in available energy, or work done by turbine. So for all four of these relation you will do the following calculation. So here we have utilized the relation. So that is the relation of h1 minus t naught s1 minus h2 minus t naught s2. So here we have different temperature and pressure values as well. So the work done by the turbine is calculated by h1 minus h2 minus t naught s1 minus s2. So as the working fluid is air, so we can use we can replace the H term with the CPT. So enthalpy is the function of temperature. So for the ideal gas we are using it as CPT. So temperature and entropy values are given. So further this relation for the change of entropy for air we have calculated in the lecture 17 as well. So we already know how to calculate the change of entropy value. So as you can remember, we have calculated three different form of change of entropy value for ideal gas, and as air is the ideal gas, so we can use either of that value. So I've already told you that one relation was between temperature and pressure, the other was between temperature and volume, and the third one was between pressure and volume. So I've told you we will use the relation according to the data provided to us in the numerical. So in the current numerical we have been given the value of temperature and pressure, so we'll use this change of entropy for ideal gas relation. So we know the values, so we know the T1, T2, T naught, Cp natural log R value for air. So the work done in turbine is 260.7 kilojoule per kg. Now for irreversibility, so here we have represented irreversibility with the capital I, that is equal to T naught del S universe. So del S universe composed of system and surrounding. So for neglecting system, so system entropy is S2 minus S1 and surrounding is a thermal energy reservoir because it is an ambient and dead state. So Q amount of heat that is leaving the system or rejected by the turbine. So the heat content of the system will decrease and the surrounding heat content will increase. So due to the transfer of heat, there will be always a entropy transfer. So entropy is transferred to the reservoir. So entropy for the reservoir is equal to Q by T naught. So similarly here we have used the ideal gas equation for the entropy change calculation. So we know all these values. When we plug in these values for Cp, T2, T1, R, P2, P1, Q, T naught, so the irreversibility value is 49.6 kilojoule per kg. So that summarizes our numerical problem. Numerical problem. A heat engine receives heat from a source at 1500 Kelvin at a rate of 700 kilowatt, and it rejects the waste heat to the medium of 320 Kelvin temperature. The measured power output of the heat engine is 320 kilowatt and the environment temperature is 25 degrees centigrade. Now you have to calculate the reversible power, the rate of irreversibility, and second law efficiency of heat engine. So this is a schematic diagram of heat engine. A heat engine is connected to the source of 1500 Kelvin temperature, absorbing 700 kilowatt of energy, producing a 320 kilowatt of work, and rejecting the rest amount of unavailable energy into the sink, that is at a temperature of 320 Kelvin temperature. Part 1, to calculate, because this is a reversible power. So for example, to calculate the reversible power, you are assuming the heat engine is a Carnot heat engine. So you will be utilizing the efficiency for Carnot heat engine. So the efficiency of Carnot heat engine is 1 minus T2 over T1, and efficiency is also equal to W over Q. To calculate the W, you will, and then the q is in the denominator on the left hand side, so it will multiply on the right hand side. So W max is equal to q into 1 minus T2 over T1. So T2 and T1 temperatures are known. So T2 is the temperature of sink and T1 is the temperature of source. So Q is the amount of energy that is entering into the heat engine. So 700, Q is equal to 700, T2 is equal to 320 Kelvin, and T1, the source temperature, is 1500 Kelvin. So the maximum work for reversible power, so power has the unit of kilowatt, so maximum work also have the unit of kilowatt. So maximum work or reversible power is equal to 550 kilowatts. So the rate of irreversibility, so irreversibility is represented with the symbol of capital I, that is equal to maximum amount of work that can be done and actual amount of work. So the difference of irreversibility is the difference of maximum work minus actual work. So actual work that is given in the statement, so actual work produced by the heat engine is 320 kilowatt, and in the previous step we have calculated the maximum amount of work. So we have assumed if the Carnot heat engine is placed over replaced by this heat engine, so it will produce 550 watt of work and actual heat engine produce 320 kilowatt of work. So the rate of irreversibility is I is equal to 230 kilowatts. Now the third question was to calculate the second law efficiency of this heat engine. So as we have derived the relation, and we know that the second law efficiency is the efficiency of actual heat engine divided by the efficiency of Carnot heat engine or reversible heat engine, that is the maximum efficiency. So the efficiency of actual heat engine is W by Q, that is 320 divided by 700, and the efficiency of maximum heat engine is 1 minus TL over TH, that is the formula to calculate the efficiency of Carnot heat engine efficiency. So TL and TH are also known. that is the temperature of sink and source. So 1 minus 320 over 1500 is the efficiency of Carnot heat engine. So when we divide both these efficiencies, so actual efficiency 320 divided by 700 and maximum efficiency, that is 1 minus 320 over 1500, then the second law efficiency came out to be 58%. So that is the last numerical for today. All students are advised to go through example problem of each topic discussed in this lecture. So you are advised to go through example problem as well as the exercise problem as well, uh, regarding the topic that are discussed during this lecture. So you are required to write a handwritten lecture summary report and send it to my email ID arsalan@cietwa.edu.pk. You are also advised to prepare this lecture thoroughly, as you may be asked question answer session. There will be when there will be online video session with you. So that is all for this lecture. Take care. Allah Hafiz.